Okay, looks like we're recording. All right. Does anybody have any questions from chapters 11 and 12 that we need to address? Anybody at all? It looks like several people didn't quite finish chapter 12. Do we need an extra day on chapter 12? Do we need to open up homework 12 until the end of today?
Could we go over question 6 on chapter 12?
Sure. We can do that. Let's have a look-see. Yes. So here we have so we have a fountain, the flow rate Q, which equals the cross-sectional area of the hose or the pipe or whatever times the velocity of the fluid. And they tell us that it's a 0.2, flow rate of 0.2, that would be 0.2 meters cubed per second, essentially. It's designed to spray a column of water 12 meters into the air. So it's going to go 12 meters in height into the air, like that. And they want to know what is the radius the fountain nozzle should have. So the fountain will have this pipe, and then it'll have a nozzle at the end of it like that. And the Q has to be the same here and here. But what we're looking for is the velocity of it coming out here. We want essentially the velocity as it comes out of the pipe to be enough, to be fast enough that it will go 12 meters high. And that's going to be a problem for kinematics, right? So in the kinematic equations, if we know how high we want it to go, and we know what its acceleration is, the acceleration is going to be gravity. Gravity is going to be accelerating it downward. So we know the height, and we know the acceleration, and we know its final velocity. We can calculate its initial velocity using the following equation. That would be velocity final equals velocity initial plus the acceleration, which in this case is g. No, that's the wrong one, sorry. I'm looking at the wrong equation here. It's similar to this though. It's velocity final squared equals velocity initial squared plus 2 times g times the height, where g is going to be negative 9.8 meters per second. So this is the kinematic equation that will tell us the final velocity, or the initial velocity, which is what we're looking for. The velocity as it comes out here is actually the initial velocity. The final velocity up here is actually equal to 0 when it gets to the top, because it stops and turns around there. So this becomes 0. And this becomes the equation that you solve for velocity initial. So it becomes, you get a negative, you subtract this from both sides. So you get negative velocity equals square root of 2 times g times h, where the g is now positive because we have a negative on both sides that we just got rid of. So you're going to plug in your number, calculate your velocity, then you put that velocity into here with the flow rate that they give you, solve for the cross-sectional area, And then the cross-sectional area is equal to 2 pi times radius, and so you solve for the radius. Or not 2 pi times radius, pi radius squared, pi r squared. There we go. So you go from kinematic equation right here to flow equation to area equation to get the radius. Does that make sense?
Yes, it does. Thank you so much.
Yeah. Anybody else have any questions about this one? I requested from our computer guys a drawing tablet for drawing things on my open math. I draw much better than I draw with my mouse or my trackpad, but they haven't gotten back to me with that. Okay, any other questions from chapter 7 or chapter 12 rather? No? All right. So we are now moving on to chapter, let's see. Let's see, we can do chapter 13 is quite a useful chapter for medical stuff. So I think we move on to chapter 13 today. And then we can come back Wednesday and decide. I think probably Wednesday we can, let's see, I don't know what we've got in chapter 16 as far as sections. Got a lot of sections actually. I'm not entirely sure that it's we could do chapter 17 without doing chapter 16, but it would take a little bit of doing, but it could be done, I suppose. I'm not really convinced that 16 and 17 are really all that valuable for people going into the medical types fields, since hearing is a very specialized field in medicine, but we'll see how we do. We'll see how we're doing on Wednesday if we feel like we want to try to cover another chapter. But let's go ahead and do the chapter 14 right now, which is not too bad as far as getting done in a quick hurry.
Will there be a final that we'll have to get done before Friday then, since class ends on Friday?
Yes, there is a final exam. Not necessarily, it doesn't necessarily have to be done on Friday. We can stretch that out till Saturday if you need to. I think they usually ask me to have my grades in by Sunday, but it just depends. Some summers they're really strict about that. Some they're not. But we should be okay, I think. Are you having do you have a scheduling issue or anything like that?
Well, I just wasn't sure. So then, will it be like go into the library and do the test like the other tests have been?
Yes, it is a test just like those. So if you're having some struggle with, some scheduling or traveling or something like that, feel free to send me an email or a call and we can try to figure that out. I often have students, taking off and going places in the summer, so something we can work around if we need to. Any other questions before we get started on chapter, whatever this is, 13, 14? All right, this is not the right one. We don't want to do 14, we want to do 13. Yeah, that's more like it. Okay, so let's go ahead and learn some stuff here in chapter 13. The reason that I like chapter 13 for people going into medical and medically related kind of fields, uh, of course, temperature is something that you do deal with quite a bit there, but we also deal with gases quite a bit. And just the idea of what temperature is and what it means turns out to be quite an important thing in many different fields. So temperature is a very interesting thing because most of us feel like we understand what it is or we know what it is, but most of us actually don't. And it doesn't even matter really how much science you've had or anything else. Temperature is something that is so ill-defined in so many ways. It's just not well understood what it is. And one of the reasons for that is because we haven't known, we didn't know really what temperature was until the past. I mean, it was only about 150, maybe not even that long ago, but just pretty recently, it was they were beginning to figure out what it was. It wasn't really until we started to understand what matter is made of, the idea of atomic matter, that matter is made of atoms, these small particles. And that was only, 100 something years ago, 150 years ago is when we started to really start to understand that and put it together. So it is it's a fairly new idea, and it's evolved kind of slowly over the decades what temperature actually is. One of the reasons that people misunderstand temperature is because of their nature. We live in a body. We live in our body that creates a lot of heat or a lot of thermal energy all the time. And the way that it does that is mostly by chemical processes, but also by movement. And really chemical processes on a microcosmic scale, when you look down at the molecular and the atomic scale, chemical processes are very much about movement of things. And it turns out that temperature is very much about movement as well, but on a microscopic scale, not on a large scale. And even though they do teach that in many science courses, and in many ways, it's not really well taught and it's not really well understood, unfortunately. And we're going to try to introduce you to a little more rigorous understanding of this. So one of the things that makes this so confusing is our personal physical manifestations and understandings of temperature and heat and things like this. So when we touch something, we perceive it to be hot or we perceive it to be cold. But what does that mean, right? Why is it that touching something is not a good idea of determining whether something is hot or cold? Can anyone think of an idea of a reason why that's not a good way to determine whether something's hot or cold?
Because it could be way too hot or way too cold and you could hurt yourself.
Okay, so there is this element of there is an element of danger. I mean, that's just not a good idea, right? There are things that can do damage to our bodies. What's a reason that it's just not a very accurate way? What if it's not too hot or not too cold and you're just touching it? Why is that not a very accurate way to measure temperature or precise? Think of people that you know. I mean, all of us have known people, met people who have very cold hands, cold skin. Some people have very warm skin. I happen to be somebody who has extremely warm skin, to the point that my wife, especially in the summertime, she's like, doesn't want to sit next to me because she can feel heat coming off of my skin. And I have a very high metabolism. I burn a lot of calories, and that creates a lot of heat my body is constantly getting rid of. And it's good that I have a high metabolism because I eat way too much food. And if I didn't have as high metabolism as I do, I'd be even fatter than I am because I burn a lot of those calories just making heat in my body. But some people are very cold. My wife is almost always cold. And this seems very counterintuitive to many people. And a lot of this is because of the science of thermodynamics is not simple. But, my wife is very thin. And so people say, well, she must have a very high metabolism. But it's not true. She doesn't have an extremely high metabolism. One of the ways that they measure metabolism is they measure your skin temperature and they measure your core temperature. Those are some of the determining factors of metabolism, because those things determine how many chemical reactions are going on inside of your body. And chemical reactions account for a lot of the energy that you're burning in your body. So what happens if I touch something that is cold compared to my wife touching something that is cold? What do you imagine I will feel compared to what she will feel? She has cold hands, I have warm hands. Can you imagine a difference there? Anybody have a thought?
It probably won't feel as cold to her.
Why not?
You have different perceptions of temperature.
Now, why do we have different perceptions of temperature? And this is the part that people really have a hard time realizing what's going on, because it's a thermodynamics thing. When we feel something that is cold and we perceive it as cold, why do we perceive it as cold? There are nerves in our hands that feel when energy moves through them. Thermal energy moving through the nerves in our hands, in other words, heat, when it's moving through the nerves in our hands can determine whether that heat is leaving our hand or entering our hand. When heat is leaving our hand, the nerves in our fingers perceive that as cold. When heat enters our hand, the nerves in our hands perceive that as hot. So heat leaving, cold, heat entering, hot. The amount of heat that leaves an object is determined by the temperature difference between the object and whatever it's in contact with. So if I have very hot hands and I touch a surface that is 0 degrees something, just 0 degrees Celsius or whatever, and the temperature difference between my hands and that surface is, let's say, 35 degrees Celsius, then a certain amount of heat will leave my hand and it'll be directly related to that temperature difference of 35 degrees. But if my wife touches the same surface and her hands have a surface temperature of 30 degrees Celsius, she will have, there will be a marked difference. It's almost 20% difference. It's almost a 20% difference in the amount of heat leaving her hand as left my hand. And so she will perceive it as 20% warmer. And yet it's the same object at the same temperature. Right? There are other things that determine how fast heat leave our hands. If you look around in your surroundings, find something that is made of wood and touch it right now with your hand. And then find something that is made of cloth or something that's made of metal, something that's a very different material than the wood, and touch it. Now, tell me which one of those feels colder.
Metal.
Metal feels colder than what?
Then wood.
So metal feels colder than wood. In fact, the metal and the wood in the room that you're in, I'm assuming they've been in that room for a while, days, weeks, months, whatever, even hours. And if they've been in the same room for that long, they're the exact same temperature. Because all things that are put in an environment, that are put in the same environment for long periods of time, all become the same temperature. It's a thing we call equilibrium. So the metal and the wood are the exact same temperature, and yet you perceive them as different temperatures. Why? Well, it turns out that metal draws heat from our hand more quickly. In other words, heat travels through metal very quickly compared to wood. So as you put your hand on the metal is colder than your hand, so heat will begin to flow, but heat flows more quickly into the metal because of the properties of metal. And when you put your hand on the wood, heat flows slower through wood, and so it flows slower out of your hand. So when you're touching things with your hands, you're not measuring temperature at all. It's not a good way to measure temperature, and sometimes it doesn't even give you an idea of anything with concerning temperature, right? Because what it's really measuring is the speed of the flow of thermal energy or heat flow, which is not temperature. What is temperature then, we have to ask? Well, if temperature is not the flow of heat, if temperature is not the difference of heat or, heat, whatever, thermal energy like we've been discussing, well, what is it? And this is the thing that was very difficult to define for a long time. But it turns out that temperature is actually an internal property of the material, and it has to be a material. It has to be something made of matter. So it is an internal energy property. It's the amount of energy that is stored kind of between the atoms, within the atoms or molecules or particles of the substance to a certain, in certain ways. And that certain way is kinetic. It's actually a movement energy that is stored between particles. Now the particles in a solid are moving. They're just not moving a lot. They're moving back and forth. They're vibrating a little bit is really what they're moving. So solids do not have a lot of movement, but they do have movement. And as that movement increases, you can actually break the bonds in a solid, and solids can become liquid. And liquids, there's a lot of movement between molecules or atoms or particles in a liquid, a lot of it. There's a lot more movement. So there's a lot more thermal energy in a liquid than in a solid. But there's thermal energies in both. And the movement in a gas is far more than a liquid, because if you add thermal energy, add heat to a liquid, you can actually make it move so fast that it flies apart and becomes a gas. Right? And this is what we call phase changing, where we're changing from solid to liquid to gas, and we can go the other way. We can slow down things or cool things off, go from gas to liquid to solid, and so on and so forth. So this temperature thing is actually a measurement of that internal kinetic energy between particles. How do we know this? We know this from many experiments that seem a little bit obtuse, that like they're not directly related to this, but one of these experiments was done by a guy named Brown, and it was Einstein that interpreted some of his experiments. But the idea is that Brown was looking under a microscope at little bits of pollen from flowers in water, floating in water. And as he looked at them very closely, he noticed that they moved around in this weird random motion, and yet there was nothing to indicate that they should be moving. Pollen, it doesn't have like flippers on it to make it move. It doesn't. It's not an animal. I mean, how does it move? What's making it move? And what he hypothesized was that the tiny particles that were in the water under his microscope were moving around and bouncing off of that pollen. And many other scientists, including Einstein, were able to further expand on that idea and create this idea that thermal energy or temperature comes from these movements, these microscopic movements of these particles. And there are many other experiments that have been done since. That's just one of the more famous ones and one of the first ones that was done. So how are we going to measure temperature if our hands don't work? And well, we need something that is not so perceptive, not perception based, but a much more solid, concrete kind of measuring method. So what we use something that reacts to temperature the same way every time in every situation, something that is repeatable, that's something that we can depend on a little bit more. There's one way to do this is to use what's called a bimetallic strip, and this is actually used quite a bit in temperature devices. You take two pieces of metal that are different, maybe copper and nickel or something like this, and you anneal them together, essentially roll them together at high temperature so that they stick together. And you make this thing called this bimetallic strip. And whatever temperature you make the strip at, it will just look like this. It'll just be a straight strip of metal. But as the metals heat up or cool down, they will expand. That's one of the things that metals do when they heat up and cool down. And as they will expand differently. One of them will expand more than the other. In this case, if the temperature is getting, as the temperature is getting hotter, this blue metal is getting longer than the gold metal. And so it starts to bend, starts to turn this way, right? And you could actually put a scale up here. You could draw a little scale up here and say, well, this one where I designed this thing, so maybe can't use my drawing tools for some reason. Here we go. You could put a scale up here and say, when this thing is just straight right here, I'm going to call that 0 degrees because I made this bimetallic strip on the coldest day of the year. And then everything over here is going to be some other different temperature. Maybe I'll call this, 70 degrees or something like that. And then this one you could call this one 90. You could make nice even marks if you wanted to, or whatever kind of scale you wanted to. You could make your own thermometer this way. And in fact, that's exactly how thermometers were made. This is how a bimetallic strip thermometer is made. And you've probably seen these kinds of thermometers. These kinds of thermometers are outside of windows all the time. People put these outside their kitchen window, and it looks kind of like a clock like this, and it has a needle on it. And it has temperatures out here, and the needle turns to show you the temperature. Well, inside the clock, what you have is actually a bimetallic spring strip. It's a spring that goes around and around like this, and this inside piece of it is connected to this needle. And as this spring gets warm or cold, it actually expands and contracts, and it turns this needle. And the scale shows you what temperature is. Another place that bimetallic strips are used are in your electrical system in your house. These are connected to a switch so that you have electricity coming through the bimetallic strip this way. And then they're connected to normally they're not hot. So the electricity is coming through like this, and it's connected to this little thing here where the electricity goes through and into the house. But if it gets too hot, so you're getting too much current through because maybe somebody stuck their finger in the socket or dropped a toaster in the bathtub or something. I don't know why anybody would have a toaster in their bathroom, but anyway, if you start drawing too much current here, then this gets hot and it bends and it disconnects from the connector here. And that's what's called a breaker switch. And it actually has a spring on it so that once it disconnects, it won't reconnect. So you have to actually go into the breaker box and flip the switch and reconnect it. And that's done so that you don't draw so much current and kill somebody. It actually doesn't work very well. It works very slowly, so you can still kill yourself with just a little amount of current that will flow through while this thing's heating up. So they've discovered new ways to block that current or to stop that current from going that work much better. And that's why in your bathrooms now you have these little switches, bathrooms and kitchens. You have these little sockets on the wall that have little buttons in them. It's what's called a ground fault interrupter. The ground fault interrupter actually stops the current before it goes through the house. So if you stick your finger in a socket, it won't draw it. The current will never get to your finger, hopefully, using a ground fault interrupter. It actually stops it before it ever gets to you, which is nice. So that's one kind of thermometer, but there are many other types of thermometers. This right here uses liquid crystals, very similar to what you have in your cell phone screens. But these liquid crystals are essentially a kind of it's a chemical. It's a liquid that changes color with different energies. The ones in your cell phone are designed to change color and brightness with electrical energy. These ones are designed to change color with thermal energy. So as it gets hot, these things start to change color. This one changes color at 95, and this one at 96, this one at 98, this one at 100, this one at 102, and this one at 104. So, and these are used often in hospitals, particularly in field hospitals. Well, they'll just stick this on the forehead, and they can just walk by and see people's temperatures from just looking at them. And they're cheap and easy to make, and everything else. This is a fireman who's using infrared light to measure temperature. So this one's a much more complex type of measuring device, but it has some electronics. It has both an emitter and a detector in here, kind of like a lamp and a camera that is looking at it's looking at the infrared spectrum of light, which is long wavelengths, longer than we can see really. So the light you're seeing there is not actually the light that it's using. It's actually looking at the light coming from here. They just have the light on there so you can see where you're pointing it. But there are other ones as well that you've probably seen, thermometers with liquid in them, for example. Mercury metal is a really good thermometer liquid. If you put mercury metal in a little bulb in a skinny little tube above it, as you heat up that bulb of mercury, it expands fairly rapidly. And as it expands into that tiny tube, it actually will jump pretty high, jump pretty quick. And then you can, put little marks on it and say, this level is this temperature, this level is this temperature, so on and so forth. You can also do it with alcohol. And those are the ones you mostly see these days. The ones with the red liquid in them are usually an alcohol. Alcohol expands pretty well with temperature. There are different scales that we use, different markings that we put on our thermometers. And the one that we're most used to here in the United States is the Fahrenheit scale, which is kind of an interesting name. In Germany, Fahrenheit means how high you will go. But it's actually the name of a scientist also in Germany. Can't remember where, but somewhere in Germany. And he essentially built a scale that was based on how hot and how cold it got in his city. So the hottest day of the year, he marked that at 100 degrees. And the coldest day of the year, he marked at 0 degrees. So it was obviously a place that doesn't get as cold and quite as hot as North Platte. So we would have a very different scale if we designed that scale. It's not very scientific, but good enough, I guess. We still use it today, obviously. Then along comes people who are trying to be much more scientific, and they make the Celsius scale. And they say, well, 0 degrees is where water is going to freeze at normal pressures, and 100 degrees is going to be where water boils, because water is super important in science. Well, it turns out it's only really important in kind of biology and a little bit in chemistry. Chemists and biologists think of water as super important. Physicists, water is interesting, but it's not really important. So to a physicist, the Celsius scale is really not any better than the Fahrenheit scale as far as science goes, because it's not really based on anything real, I guess, anything that has real meaning to a physicist. But once physicists started to realize that their theory that temperature was based on movement of particles, then they figured out that if particles stop moving, the temperature will be as low as it can be. In other words, there is a zero temperature. There's such thing as a zero. With the Celsius and the Fahrenheit scale, the people who developed those never imagined that there is a coldest temperature that you can possibly go. They never imagined that. But physicists figured it out. In fact, it was Lord Kelvin that actually calculated what that would be. And the way that he did it is he took a bunch of different gases and he cooled them off, and he watched as their pressures went down. Well, pressure, of course, is force from movement of particles. And he measured the pressure going down in different gases as their temperatures went down and down and down and down. And he got them as cold as he could. And then he just extended those lines down to the point where the pressure would equal zero, where there would be no force from the particles of the gas. And he just extended those lines all the way down to zero. And what he discovered is that if you go negative 459 degrees Fahrenheit or negative 273.15 degrees Celsius, you actually will reach the absolute coldest temperature you can get to, which we call absolute zero. And the Kelvin scale uses the same size degrees as the Celsius scale, but it starts at 0, 273.15 degrees Celsius below 0 degrees Celsius. So 0 Kelvin is the absolute 0 point of temperature. You may ask, how cold have we ever gotten anything? Well, I can tell you one thing. We don't get anywhere near 0 Kelvin using any kind of refrigeration technique. It is impossible to get very close to 0 Kelvin using any kind of refrigerator, because refrigerators, what they do is they remove heat by bringing something cold near to it. Well, something colder near to it. Well, if you're trying to get to 0 Kelvin, there's nothing colder than 0 Kelvin. And there's really nothing even close to 0 Kelvin that exists in our universe. So the only way that they can do it is they manipulate atoms using lasers. They slow atoms down and slow them down and slow them down using lasers until they can get them down to about 0.000000001 Kelvin, which is 0.1 nanokelvin or something like that. It's super low. Or it's 0.1 nanokelvin or 0.1 microkelvin. I can't remember, but it's a lot of zeros that they are going down to. I think it's 0.01 microkelvins, 0.000000001, whatever, it doesn't matter. And they do that using lasers and magnetic fields, but they can only do it for a few million atoms, which is a very small number of atoms. It's almost unmeasurable. But they have done it, and they've actually used it to advance a lot of really interesting technologies and sciences. So, in fact, in the laboratory I worked in, we were able to get down to 2 millikelvin, 0.002 Kelvin, so very close to absolute zero, but not nearly as close as some other laboratories. We were working with a large atom, which is very difficult to cool down. But anyway, if you want to go back and forth between these temperature scales, these are the conversion equations from Celsius to Fahrenheit, Fahrenheit to Celsius, Celsius to Kelvin, Kelvin to Celsius, and so on and so on and so on. So you can use all these formulas to convert back and forth. Here they do a conversion at room temperature. So room temperature is about 25 degrees Celsius. In Fahrenheit, they use the Fahrenheit equation, and it's about 77 degrees Fahrenheit. In Kelvin, it's about 298 Kelvin, turns out. And there's even another scale called the Réaumur scale, which is a French one, I think. But the Réaumur scale is, I don't know. This is the conversion though for the Réaumur scale. Anyway, at the relativistic heavy ion collider is where we've reached the highest temperatures known in the universe, 10 to the 12 Kelvin. The interior of a neutron star, which is about as hot as it gets in the universe naturally, is about 10 to the 9. So we can get about 1,000 times hotter than the universe does. Our sun is about 100 times less than a neutron star. A neutron star is like a black hole, kind of like a baby black hole. So that's 100 times hotter than our sun. Center of the Earth is actually pretty hot. Right here. Surface of the sun is actually cooler than the center of the Earth. Fireplace fire. This is a logarithmic scale, so each one of these ticks is 10 times bigger than the last one. So you can see this is where we live right about here. We live right about here, about 10 to the 2. So here's actually a graph of what Lord Kelvin did, where he cooled down all these gases and then he extended the lines down, and noticed that zero pressure is reached at the same temperature for all of these gases at negative 273.15 degrees Celsius. And this is where we get to the very first law of temperature that we're going to talk about, which is the law of what's called the 0th law of thermodynamics. Hold on a second. My computer is about to die and I don't know why. It's charging now. I don't know why it wasn't before. It's about to die. So anyway, the 0th law of thermodynamics is called the 0th law because they developed the first and second law and then realized that the 0th law was more fundamental. And so they wanted it to be the first one, but the first one was already named the first one. So they called it the 0th one. This is how physicists work. Physicists just, you know, we don't care if we have to call something the 0th law, we just do it. So anyway, the 0th law says that if you have two things that are in thermal equilibrium, in other words, take two objects, put them in a room and let them come to the same temperature, and then you have another third object and you bring it in contact with those two, and they're all in equilibrium, then the first object's going to be in equilibrium with the last one, even if the last one was only in equilibrium. It doesn't really matter. What it's really talking about here is that things, when they're brought into contact with each other thermally, they can trade heat back and forth. Eventually, they're going to all become the same temperature. And that actually becomes quite important in many things. We're not going to spend a lot of time thinking about that because we're not going to do thermodynamics, which some students will do as they go on to the next chapter. So I already mentioned that materials stretch and shrink as they heat and cool. Some do the opposite, actually. Some objects actually shrink as they get hot and stretch as they cool. But this is actually responsible for many things you've probably seen in your everyday life. For example, the reason that they cut seams in the concrete is because of this, because concrete stretches and shrinks as it gets hot and cold. If it stretches and shrinks without the seams in the concrete, then it will just break up into all kinds of pieces. But if you put a seam in the concrete, it'll break at that seam and will be less likely to break other places. They often fill the seams with rubber as well, and that actually allows them to expand without breaking each other. Sometimes they put a big gap in between roadways and fill it with rubber so that the roadway can expand. You'll see that on bridges a lot. Here on a bridge, you can actually see this metal plate that has these teeth on it that allows expansion. As this expands, these teeth go into these grooves here, and as it retracts, it looks more like this. But these teeth prevent the road pieces from slipping apart. And so these are called expansion joints. And expansion joints are everywhere. They're in houses, they're in roads, they're in buildings of all kinds. How do these things expand? Well, this is the law of linear expansion, or the equation for linear expansion in one dimension. As things expand along a straight line, they expand depending on the change in temperature. So it includes the change in temperature. It also depends on the original length. The original length of the object determines how much it's going to stretch. So a longer object will stretch more. But it also depends on the material. The material has a coefficient of linear expansion called alpha, and every material is different. So you have to have a chart of materials and their coefficients of linear expansion. Aluminum, it's 25 times 10 to the minus 6, which is 25 microns essentially. So for every meter, aluminum will gain 25 micrometers in length for every meter for every degree Celsius. And for brass, it's less. For copper, less. Gold is less. Iron, steel, less. So aluminum expands quite a bit. Lead expands even more, right? Glass expands very little. Concrete expands a fair amount, actually. So those are the linear coefficients of some different materials. And do an example here with the Golden Gate Bridge, the bridge that I grew up with. So you have 1,275 meters when the bridge is cold, and then it changes temperature from -15 to 40 degrees. They want to know the change in length. Well, we need to know the change in temperature. Whenever you're doing using equations that use a change in temperature, then usually you're going to use Celsius or Kelvin. If it just is an equation that just has temperature, not change in temperature, then you need to make sure that you're using Kelvin almost all the time. But change in temperature can be Celsius or Kelvin because it's the same amount of change, whether you're using Celsius or Kelvin. So change in temperature is temperature final minus temperature initial. So you take the 40, you subtract off the -15, you get a change in temperature of 55. Original length of the bridge is 1275. And we're going to use the coefficient of expansion for steel, which is, are they using steel or concrete? Yeah, they're using steel. So there it is right there. So they plug in those numbers and it's 0.84 meters, nearly an entire meter of stretch in that bridge as it goes from its coldest to its hottest. And you can see that happen if you draw, a mark on the ground and then watch that, because this change in temperature can actually happen in a single day in San Francisco. In San Francisco, and especially this time of year in August, you can wake up in the morning with fog and really cold temperatures, and then that afternoon it can be really hot. It can be 100 degrees out. So that can be observed in a single day. So how they do that is at the end of the bridge. If you've ever been over a long bridge, you'll actually see this. At the end of the bridge, there's kind of a seam in the bridge that you drive over, where you're driving over a plate of metal essentially, and that's where the road of the bridge actually dives underneath the entrance to the bridge from the land, so that the roadway can expand that meter or so that it needs to expand as it heats up. And there are also all the expansion joints on the bridge. But expansion doesn't just happen in one dimension. In reality, it happens in all dimensions. So in 2 dimensions, what happens? Well, it's kind of interesting because it's not generally intuitive. If you have a plate, like a solid square plate like this, and it expands in 2 dimensions, it just gets bigger in both dimensions. It gets longer, it gets wider. But if you cut a hole in the plate, a lot of people would think, oh, well, if it expands in both directions, then that hole is going to get smaller. But it doesn't. The hole actually gets bigger. It expands outward in both dimensions, but it doesn't expand inward. So the hole actually gets bigger. And if you're in 3 dimensions, so that you have, a height, a width, and a depth, then the whole volume will get bigger or smaller if it's getting colder. For 2-dimensional expansion, the coefficient of expansion is usually just twice the linear coefficient of expansion. So you just go back to this chart and say, oh, the coefficient of expansion for glass is 9 times 10 to the minus 6. So in 2 dimensions, it'll just be 2 times that. In 3 dimensions, usually it's 3 times the linear dimension, but not always. It's not exactly that all the time. So an example of that would be right here, iron and steel. The 3-dimensional expansion is actually a little bit less than 3 times the linear expansion. And so they give you the coefficient of volume expansion here. The equations for expansion in 2 dimensions and 3 dimensions are the same as the ones in 1 dimension. And it's just a different coefficient. So instead of for area, for 2 dimensions, you get change in area equals 2 times alpha times area delta t. There is that 2 times alpha. And then in volume, it's change in volume equals beta, or 3 times alpha times the original volume times delta t. So all those equations are pretty much the same equation with just a 2 and a 3 added in, multiplied in. So one of the things that's interesting about water is its molecular structure creates an interesting situation when it freezes. And all of us are very familiar with ice floating in liquid water. And we hopefully understand the reason for that. The reason for that is because as water, liquid water, begins to freeze, it goes through an interesting cycle of density. So here is the temperature of water on this scale, and this is the density of water. So this is liquid water right here. At 12 degrees Celsius, it has a density of 0.99950. As it gets colder, it actually increases its density because the molecules are getting closer and closer together. They're packing tighter in. You get colder, it gets more and more dense. So if you're a chunk of water sitting in a lake, as it gets colder and colder and colder, you're essentially getting more and more and more dense. And as you become more dense, it's like you have more mass stuck into the smaller space. So you will sink below other water that is less dense. You're going to sink below water that's warmer. So as a lake is cooling, the cold water on the top begins to sink to the bottom of the lake, and the warm water at the bottom of the lake begins to come up to the top of the lake. And it just kind of cycles as the water gets colder and colder and colder, and the water gets more and more and more dense, right until it gets to be about 4 degrees Celsius. When it becomes 4 degrees Celsius, the polar nature of the molecules of water begin to push against each other and start to expand out. And the water actually gets less dense as it begins to freeze, as it begins to become solid. It becomes less dense. So the cycle of cold water sinking to the bottom and warm water coming to the top and cooling off, and then sinking to the bottom and then cooling off, this cycle actually begins to stop once it stops once you get to 4 degrees. Once the whole lake reaches 4 degrees, then the water stops cycling from the top down. And the water on the top starts to become colder, and it actually, instead of sinking, it actually stays on top, it floats. And that's why water freezes from the top down. That's why you get a lake that's frozen on top and liquid underneath, because the water underneath is more dense than the colder water on top. So it's never going to float up to the top because it stays below the colder water on top, right? So the water underneath the ice is always warmer than the water on top, within the ice itself. Eventually it will all cool off and freeze all the way to the bottom of the lake if you have a long enough winter. But if you don't have a long enough winter and your lake is just too deep for that, then that water underneath the ice just kind of stays there. And if you have a really deep lake, for example, Lake Tahoe is thousands of feet deep. It's so deep. It's a lake in the mountains of California. The surface of the lake is like at, I don't know, 12, 13,000 feet or something like this. But it is a super deep lake. I think it's 6,000 or 7,000 feet deep. So it actually is half the height of the Sierra Nevada mountains deep. It's so deep, and it's a natural lake. It's been there for probably 1 billion years. The water at the bottom of Lake Tahoe is 4 degrees Celsius. There's no question, because as the water has cooled down at the top of the lake and it gets more and more dense and it starts to sink down to the bottom, that 4 degree water just sinks all the way to the bottom of the lake. It did it 1 billion years ago. It sank down to the bottom of the lake because 4 degree water is the most dense water that there is. If you get any colder than that, you get less dense. If you get any warmer than that, you get less dense, and then you rise to the top again. So that 4 degree water fell to the bottom of the Lake of Tahoe 4 billion years ago, and it's been, or like 1 billion years ago, and it's been sitting there doing nothing for that long. And for that reason, scientists go to Lake Tahoe and other very deep lakes to study the bottoms of the lakes, because the bottoms of those lakes have not been touched for 1 billion years. Nothing has gone down there and nothing has come up. It's just been sitting there for 1 billion years, which is super cool, of course. Maybe not 1 billion years, maybe a little bit less than that, maybe millions of years, who knows. But anyway, really interesting stuff. But this is why water freezes from the top down. That is not true of most liquids. Most liquids do not freeze from the bottom down. They will actually freeze from the bottom up. So if you had a lake filled with methanol, for example, it would, and it froze in the wintertime, it would freeze from the bottom up instead of the top down. because as its liquid got colder and colder and colder, it would sink to the bottom and keep sinking to the bottom. And the colder liquid would always sink to the bottom, so that when it finally got to its freezing point, it would, the coldest stuff would be at the bottom and would freeze from there up to the top. Very different than water. Water is interesting in that way. So here's a problem where we're going to fill a tank with gasoline in the morning, and then it's going to get hot and expand. And we fill the tank all the way to the top. We're going to figure out how much we're going to spill. So we got a 60-liter tank. It's full of gas at 15 degrees Celsius, and then it warms up to 35 degrees Celsius. So that's a change in volume. How much change in volume are we going to have in the gas? That's going to be the beta of the gas times the original volume of the gas times the change in temperature. And the spill will just be the difference between the original volume and the change in volume. And so you lose 1.1 liters. That's why you don't fill up your tank more than it should. You know, the automatic turnoff valves at the gas station are designed to leave some space at the top of the tank for expansion. If you're one of those people that likes to get as much gas in there as possible by pulling the thing out and filling it just a little bit more, what you actually are doing, especially on hot days, is you're just spilling gas while you're driving, which is not only a waste of money, but it's just not safe. The interesting thing is we freak out so much about gasoline, and yet we pay for drinking water. Most drinking water that you pay for comes from the tap, like 99% of it, even the ones that say pure water or spring water. It's been actually proven that most bottled water, even the expensive stuff from like Sweden or whatever, it just comes out of a tap somewhere. And we pay, you know, for a small bottle of that, we'll pay $1 or $2 or sometimes even like $5, crazy places. And that ends up costing like 50 times as much as gasoline costs. And yet we freak out over, you know, a couple of cents per gallon in a gas at a gas station. And then at the same gas station, we'll pay $3 for or we'll pay, another great one is pay $6 for a cup of coffee. A cup of coffee at best, the most expensive coffee on earth, costs about 2 pennies per gallon at best, at the most. And water costs like 2 pennies for 50 gallons or 150 gallons. It costs so little, yet we pay so much for it, which is just hilarious. Bottled water is the most expensive liquid on the planet today, by far, which is just hilarious. So anyway, I actually have a bunch of bottled water. I have a bunch of sturdy water bottles that I've collected over the years from when people have just given me a free water bottle. And I just fill them with tap water and put them in my fridge so I have cold water to drink. Here you can actually calculate the stress on the tank using one of our previous examples of stress and strain. So the change in volume actually creates a pressure, which is something we learned in the last chapter, I believe, that we did, or maybe 2 chapters before, I can't remember. But they essentially combine the equation. They take the change in volume and put it into the strain equation and then solve for the amount of pressure in the equation, which is the force over the area. And turns out the pressure is pretty significant. It's 100 times the pressure in, it's 100 times the pressure that is outside. The gas tank would actually burst if it didn't have a way of relieving that pressure. Most gas tanks just don't seal. You know, you think that your gas tank will just seal, but it doesn't seal. It actually has a valve on it or just an open port on it that allows gasoline to spill out if it needs to. If it didn't, if you could seal it up really tight, then your gas tank would just explode with that much gas in it and just rupture. Then you'd have a real problem. Potholes are also caused by expanding concrete or expanding blacktop and contracting, expanding, contracting. Eventually it just leaves a hole. So that takes us to the ideal gas law. So let's see, how many sections do we have here? So when we're talking about gases in particular, there's a lot of study that's been done on gases, mostly because we live within a gaseous environment. And so it just makes sense to understand that as much as possible. And there are a lot of laws that are associated with gases, but there's really one law that covers everything. So all the laws associated with gases are combined to make this one equation, this one law. And it's really quite simple. Here we have this example where we have this tire that we're measuring the pressure of. And if you have a tire and you add air to it, the pressure actually increases because there's more air molecules pushing on the tire. So there's more force, so there's more pressure. But you can have the same thing happen. You can increase the pressure by increasing the temperature. So if you're driving down the road and you're heating up your tires, the air pressure in your tires actually increases. Well, why? Because temperature means that the particles in the air in your tire are moving more quickly. So they're hitting the tire more often. So there's more force on the tire. So that's more pressure. So you can either add air or add temperature, add heat, and that affect both of those things increase the pressure. You can also change the volume of the tire. So if you take this same tire and instead of just adding air, you just squeeze it into a smaller tire. You make it into a smaller tire with the same amount of air in it. Then that will also increase the pressure. So you have three things that affect the pressure in a tire. You can change the temperature, you can change the amount of gas inside of it, or you can change the volume. And the ideal gas law accounts for all three of those things in one law. And it looks like this. The pressure times the volume equals the number of particles in the gas times the temperature times this K thing that we call the Boltzmann constant, named after Ludwig Boltzmann, who did a lot of work with this stuff. So you can see here that if we solve this for pressure and divide by volume on both sides, then increasing the number of gas, the amount of gas, the number here, will increase the pressure. Increasing the temperature will increase the pressure, and decreasing the volume will increase the pressure if we divide by volume. So that's the ideal gas law. Why is it called the ideal gas law? Because the ideal gas law assumes that the gas obeys a couple of rules we call the ideal gas rules, or the rules of an ideal gas. In an ideal gas, the particles will not interact with each other at all. So there's no forces between the molecules, really, no bouncing off each other or anything like that. It also assumes that you can't, let's see, what's the other one? I think that's pretty much it, actually. That there's no forces really. There's no interaction between the particles, and I can't remember if there's any other rules for the ideal gas. But anyway, that's why it's called the ideal gas law. So here they do a tire pressure example where they have a bicycle tire with a pressure of 7 times 10 to the 5th Pascal. That's an absolute pressure, so that's above absolute zero pressure. And the temperature is 18 degrees Celsius, and they're going to change the temperature to 35 degrees Celsius. So if you have the same pressure and you change the temperature, how is that going to change this thing? Well, one way that you can use the ideal gas law is to use it as a ratio of final over initial, or initial over final. So here we have the final pressure and the final volume over the initial pressure, initial volume, and that's equal to the final number of molecules times the Boltzmann constant times the final temperature, and then the initial over the initial number of particles times the Boltzmann constant times the initial temperature. And then you just go through here and you say, well, in this particular problem, we're talking about a tire where we change the temperature, but that's the only thing we change. We don't change the K constant never changes, but we're also not changing the amount of gas. So that the N over the N is the same, it's one number over the same number. So that just becomes 1, the K over K becomes 1. We're not going to change the volume, so the volume final and the volume initial becomes 1. And we're just left with this equation: pressure final over pressure initial equals temperature final over temperature initial. And that's one way to use the ideal gas law, is when you're going from one to another, from an initial to a final, then you can use this ratio version of the ideal gas law, where you have one ideal gas law over another ideal gas law at 2 different points in time. In this case, you just solve for that final pressure and plug in the numbers. It's pretty simple. Make sure, though, these are not changes in temperature. This is temperature final over temperature initial, not temperature final minus temperature initial. So you need to have them in Kelvin. So you need to convert the Celsius to Kelvin by adding 273 to both, and then you can get the final pressure. Now, there's another way to use the ideal gas law, and that is if they just give you a bunch of stuff and there's one thing that you want to know from the ideal gas law. In this case, we're just calculating the number of molecules in a cubic meter of gas, and that's fine. They tell us the temperature is 0 degrees, so that's 273 Kelvin. They tell us the pressure is just atmospheric pressure, which is 1 times 10 to the 5th Pascal. They tell us the volume is 1 meter, and then of course we know that Boltzmann's constant is just what it is. And they want us to calculate the number of molecules. So you take the ideal gas law and solve it for N, and we get this equation right here, and then plug in those numbers. Turns out it's a lot of molecules. There's also another way to write the ideal gas law. In the first version of the ideal gas law, this big N is the actual number of molecules. And so it's a big number. That's a big N, it's a big number, so that makes sense. But particularly, chemists prefer to work in number of moles. A mole is 6.02 times 10 to the 23rd particles, or stuff. It's like a chemist's dozen, like a baker's dozen is 13. A chemist's dozen is a much bigger number. So it's a huge number of molecules, and it's based on carbon again, which is not really all that scientific. It makes sense for biologists and chemists, but it doesn't make any sense for anybody else. But it's okay. We can rewrite the equation. The only thing that's going to change in the equation is this N. This big N is now going to become a different thing. We're going to use a little n instead of a big N. And because we're putting in a different number here, we're going to have a different constant to make this work. And so the new equation looks like this. PV equals little n times R times T, where R is called the gas constant and N is number of moles. So if N is equal to 1, then your big N would be equal to 6.02 times 10 to the 23rd. So little n is a smaller number now, but it's a number of moles. It's not a number of molecules. Moles is a huge number of molecules. So R is equal to it turns out, a much different number. So it's just a different version of the ideal gas law. And because it's used in chemistry a lot, they actually have their own version of it because they use calories instead of joules, and they like to use moles, and they also like to use liters. So they have a different version of it here. It gets really confusing to people who prefer to just have one equation, but whatever. So they do the same thing here with the bike tire, but they do it with number of moles. We have a number of so how do we figure out the number of molecules? To figure out the number of number of moles, if you know the number of molecules, you have to take the number of molecules per meter cubed and divide by the number of moles per molecules per mole rather, and then you find out the number of moles per meter cubed, whatever. It's essentially a conversion here. If you've never done that in chemistry before, then you'll definitely want to practice that once or twice. But down here, we know the pressure, we know the volume, we know the temperature, we know R, and we're just calculating the number of moles. So it turns out to be half a mole, a little bit more than half a mole, which is a lot of molecules. To find the number of molecules, you'd multiply this times 6.0 times 10 to the 23rd, which gives you, like probably 3.9 times 10 to the 23rd, a pretty big number. Another interesting thing about the ideal gas law is that the pressure times the volume is actually, it actually has the same units as energy. So the ideal gas law on both sides is equal to energy. It's like thermal energy, you can think of it as. Pressure times volume is an energy, the NKT is an energy, nRT is an energy, and that becomes quite important in later things here. Now we get to the physics version of all of this. If temperature really is the movement of small particles in a gas, then why don't we just figure it out? Why don't we just figure out how it's related to that movement directly? So we do a thought experiment. We say, what if we just look at one particle and imagine that one particle comes in and just hits the wall of a tire or something that we're thinking about. So here's that one particle coming in, bounces off the wall, comes back this way. It's going to have a change. It's going to have an initial velocity and a final velocity. And the relationship between those initial velocities and that final velocity, we can calculate the force, because change in momentum is equal to force. Change in velocity times mass is equal to force times time. We know that from a previous chapter. And so they actually do that. Well, we also know that there's energy involved, and we know that pressure times volume is actually an energy. So when we do this, we actually figure out something really interesting and cool. And they don't go through this in great detail here, but I think they do down here a little bit. So let's move down a little bit, and yeah, here it is. So let's see, that's not where it is. I think they do this part backwards, but that's okay. Well, maybe they don't do it at all. Kind of do it in this example. They do part of it in this example anyway. Okay, so here it is. Force is equal to the change in momentum over time. The change in momentum as it bounces off this wall is going to be determined. We actually did this in a previous chapter. So it essentially ends up being twice the velocity times the mass. So that's where they get this twice the mass, twice the velocity times the mass, or 2mv in the x direction, divided by time. And then you multiply by time on both sides eventually. Well, actually they don't. So here they have 2mv x over delta t. The delta t, the time that goes by, is the change in distance that they travel, which we're going to call L, times or divided by the velocity. So they put that in place of the time down here. And you can see here that a 2L divided by V down here is going to be the same as multiplying by V on the top. So they move that V to the top. The 2's cancel out, and you get mv squared divided by L. Well, mv squared kind of looks like kinetic energy. Remember, 1/2 mv squared is kinetic energy. So let's go ahead into it. So what if so that's just for one particle. If you have many particles, then you multiply by n to get all these particles, and you take the average velocity. So that works. And if you have 3 dimensions, then you get one of these velocities in each dimension. So it's like multiplying by 3 on the energy side. So you get 3 times the energy. And then if you do that, you end up with this kind of deal, where the force is equal to the number of molecules times the average velocity squared times the mass divided by 3 times L. Well, again, this looks very much like kinetic energy, and it definitely has the same units as energy in the end. How does it have the same units as energy? Well, there's an L here, and we do this pressure. We take pressure equals force over area, and then we're going to get rid of this L by multiplying it by it on both sides. Oh, no, we're not. We're actually going to divide by the area on both sides. And then when we divide by the area on both sides, we're going to get the area times the length, which is the volume. And then we multiply by the volume on both sides, and we get P times V. Well, that looks like the left side of the ideal gas law. Now, just in case you're wondering, you don't need to remember all this. You only need to remember the result. But this is to just show you that how this came about. This was actually worked through using kinematics. It was worked through using essentially the ideas of kinematics and Newton's second law and momentum. So all this came from essentially momentum and force, and it got us to pressure times volume, which is the left side of the ideal gas law. But on the right side, it's not equal to nRT or nKT. It's equal to 1/3 N mv squared, which looks kind of like kinetic energy. Not exactly, but it's pretty close, right? Well, if this is equal to P times V, then it's also equal to nKT right here, or nRT. And if that's true, then we can actually define temperature. We can solve this for T. And you can get an equation for temperature that actually includes velocity of the particles, the average velocity of the particles, which is what they do down here. So the average velocity of the particles is equal to the square root of 3 times K times the temperature in Kelvin divided by the mass of the particles. And you can also flip this around so that you have the temperature equaling velocity of the particles. And in this example, they actually calculate, they're going to calculate the kinetic energy and the speed of a gas molecule. The kinetic energy of a particular molecule is just 1/2 mv squared, but that's also equal to 3/2 kT. Because of what we did previously when we ended up with that 3 times n times m times v squared. So this right here is an equation to remember that the average kinetic energy in a gas is 1/2 mv squared of the average velocity of the particles, but it's also equal to 3/2 times the K constant times temperature, Boltzmann constant times temperature. And it's also good to remember that the average velocity equation, which is this one here, those are two very important equations. So they go ahead and calculate the kinetic energy using the temperature, because that's the easier one to do. They know the temperature, they know what K is, 3/2 is easy, plug it in, there's the kinetic energy, the average kinetic energy of the gas. To solve for the average velocity, 3 kT over m square root, boom. And they actually end up solving for the mass. No, so they calculate the mass from the periodic table. If you don't know how to calculate the mass from the periodic table, I think we went over this once before, but if you don't know how, then you need to go to the periodic table and get the atomic mass off of the table, which is usually the number that it's not the number that's just a whole number, it's the number that has some decimals to it, and is usually about twice the whole number being the mass number. Is that right? No, the atomic number, I can't remember which one is which. But anyway, you have one number that's the whole number that just goes 1, 2, 3, 4, 5 along the periodic table. And then you have the number that is the, that tells you the, it essentially tells you the average number of nucleons in the thing. And that's the one you want to use. And then you multiply that, that's the number of kilograms. If you multiply that by 10 to the minus 3, you get that as kilograms per mole. And then you divide that by the number of molecules per mole, and you will get the amount of mass. So that's what they've done here. And they actually multiplied by 2 because they have 2 nitrogen atoms, and this is the molecular mass. So they call that the mass of a nitrogen. This is called the atomic mass. The other one's called the atomic number or the mass number or something like that. I don't know what they call it. That's why I'm not a very good chemist. Anyway, so then they use the equation for the velocity there and calculate the velocity. It turns out to be a fairly high velocity for molecules in a gas. And this one's actually a low one. This one's 511 meters per second, but they can be in the thousands easily. And remember that is an average. So if you look at a sample of gas, most of the molecules will be running at that average, but some of them will be going much faster, not many, but some, and some will be going much slower. And it kind of floats along this bell curve where your average molecules are all right in here, and then there's these outliers here on either end. The interesting thing is as you get hotter and hotter and hotter, this curve actually begins to really flatten out. It gets wider and wider and wider. So the hotter you get, the more distribution you get in these particles. And the colder you get, the tighter it gets. So the more of them are closer to the average. And that's actually been used. That was used to make this idea of this bell curve, essentially, I guess, was used to actually make these super cold gases using lasers. Essentially, what they did is they used lasers to cool it down so that this curve became extremely skinny and extremely steep. And then they essentially dumped out all the atoms that were on the peak and only kept the coldest atoms that are down at this tiny little end here. And that's how they were able to get to the very coldest temperature that we've ever reached in science. So here's an interesting thing. In order to escape Earth's gravity, an object must be going 11.1 kilometers per second. Pretty fast, 11,000 meters per second is how fast you have to be going to get away from Earth, to escape Earth's gravity when you're at the top of the atmosphere. So what temperature does helium have to be to have that RMS speed? Well, the mass, to get the mass, we take the molar mass over the number of atoms per mole. They call that molar mass, I guess, if they call that, not atomic mass. But anyway, the molar mass of helium, you can get that from there. And then we're going to go ahead and use either this equation or this equation to calculate temperature. They go ahead and do the first one. Calculate the molar mass from the periodic table. Then calculate the temperature, 1.98 times 10 to the 4 Kelvin. And this is way higher than than helium gets in our atmosphere, and it's way higher than anything gets in our atmosphere. That's very hot. But when the Earth was young, the temperature of the atmosphere was hotter, and so helium actually left much more easily. So it's very difficult to find helium in our atmosphere. There's helium on Earth, but not in our atmosphere. Of course, the moon is much smaller, and so has a much lower escape velocity. And there aren't any gases that stay on the moon. The moon has no atmosphere because you don't have to be going very fast to get off the moon. It takes very little, takes a very low speed to get off to escape from the moon's gravity. Okay, we're almost there. We're on phase changes. I think we have just 2 sections left. So what are phase changes? Phase changes are the change between liquid and gas and liquid and solid as the temperature changes in a particular material. And ideally, as scientists, we would like to see these things happen very cleanly, but they don't. It turns out that it's not very clean at all. Here is a gas that's changing temperature, and you would expect as it goes colder and colder and colder to just its volume to just condense and condense and condense. But what happens though is when it gets to a liquid, when it starts to condense into a liquid, it drops in volume dramatically, right? So the gas behaves pretty nicely, but the liquid, it drops at that stage, it drops really dramatically. And then when it goes to a solid, it drops a little bit less, but it's still pretty dramatic. And why is that? That's because the density of liquids. Gases are much further apart, so the volume is going to be much higher and it's going to change much more. But once it condenses into a liquid, or once it goes from a liquid to a gas, there's going to be a big jump as those molecules get much further apart as they go to a gas, or much closer together as they go to a liquid. And then it gets a little bit closer together as they become solid. So there's not that, there's these big jumps in the graph. We call these things PV diagrams because this one's a VT diagram, a temperature volume or volume temperature diagram. But we also look at PV diagrams. We actually look at many diagrams with the ideal gas law. With PV diagrams, you can see the pressure or the volume, the pressure as a function of the volume here. And you have these different zones, like this is right here is the liquid zone. So actually this is the liquid vapor region. This is where it's changing from liquid to vapor. This outside of it is liquid, and then, sorry, this to the left is liquid, this to the right is vapor. And actually, one of the main reasons for studying these things is to study kind of the behavior of these things as they get close to this region where they turn into a liquid, and they have this mixture of liquid and vapor. You see this liquid and vapor region in our everyday lives all the time. Whenever you boil water, for example, you have liquid water and gaseous water. The bubbles in the boiling water are not made of air. They're made of liquid, they're made of gaseous water. The gas inside those bubbles when you boil water is actually water gas, not air. Air is nitrogen and oxygen, other things. So that's a mixture of liquid and vapor, and that's what this region is. But they're mostly here to kind of study these things that happen outside of that region as you get these little bumps. Not very interesting necessarily for this class, but they are used. One of the things that we learn is that if you hold the temperature steady, that these phase changes happen at specific temperatures for a particular pressure. And you can also hold the temperature steady and then change the pressure and have these things happen. So you can actually boil water at 0 degrees Celsius. You can make it boil when it's supposed to be freezing. To do that, you have to lower the pressure, though. You have to essentially lower the pressure above the liquid to a very, very low pressure. And this is actually kind of interesting for people who climb mountains, for example. My father was a mountain climber, and I did a fair amount of mountain climbing with him. And when we would climb, the first mountain I climbed was an 11,000-foot volcano in California. And as you get up to those higher altitudes and you boil water to make your dinner, the water boils at a much lower temperature because the pressure is lower. So you can boil water at a temperature of that's not even that hot. So you're eating like ramen that's kind of lukewarm, essentially. But the water was boiling when you made it. And sometimes your noodles are crunchy because it's not quite hot enough to cook the noodles very quickly, and you just kind of soak the noodles and wait for them to just get a little mushy from soaking or whatever. So that's the idea here, is that the pressure, the temperature and the pressure play a role in this. And every substance is different. And they have these things in here, these critical temperatures and critical pressures are things that are determined by studying these graphs. Again, they're useful in many scientific ways, but we're not going to really use them that much here. What we will use is this is a pressure temperature graph. So I told you we use several different ones. Here's a volume temperature graph. Here's a pressure volume graph, and here's a pressure temperature graph. This one shows an interesting thing in that it splits the solid, liquid, and vapor region into three very defined regions. This is for water. If you're in this region here with these temperatures and these pressures, you're going to be a solid water. It's going to be ice. If you're in this region here with these pressures and these temperatures, it's going to be a vapor. And you have to raise that pressure and have these kind of temperatures to get into liquid. But there's this point here where they all meet. And at this point, if you can reach this pressure, which is 0.006 atmospheres, and this temperature, which is 0.01 Celsius, you can actually have liquid, solid, and vapor all at the same time. In other words, you could have a glass with ice floating in it, and it'd be boiling water. You'd have a glass of liquid water that is boiling and has ice floating in it at that, if you're at 0.006 atmospheres and 0.01 degrees Celsius. So that's kind of interesting. It's difficult to get to that temperature and pressure, but for carbon dioxide, it's much easier. For carbon dioxide, but you need to reach a temperature that's like room temperature, a little bit above room temperature, and a pressure that's pretty high, like 100 psi. So what you do is you put dry ice inside of a very strong container and seal it up and just let it sit around. And then you will end up with liquid carbon dioxide. The dry ice will actually melt into a liquid. It'll melt into liquid carbon dioxide, and that liquid carbon dioxide will boil, and you will have some dry ice sitting in it. It won't be floating in it because dry ice doesn't float in liquid carbon dioxide. It sinks. And that's something that's kind of cool. Whenever you're dealing with these transitions from liquid to solid to gas to liquid, whatever these transitions, you often reach a point where the transition is actually going both ways. We call this equilibrium. In fact, it's always going both ways, but most of the time it's going faster one way than the other. But sometimes you reach this equilibrium point where it's going the same speed in both directions. You're creating just as much ice as you're melting or whatever. And that's what's called equilibrium. These equilibriums happen at certain temperatures for certain materials. For water, the equilibrium is just above 0 degrees Celsius when you're freezing the water. So as it's freezing or as it's melting, one or the other, at 0 degrees Celsius, you can actually get this, you can get this amount of water that's freezing and amount of water that's melting that is equal. It's at about 0.01 Celsius and a 0.006 atmosphere is where that happens. So just above normal, actually it's pretty low, it's pretty low pressure where that happens, and just above freezing, just tiny bit above freezing where that happens. For carbon dioxide, it's a much different place, 5 atmospheres and negative 56 degrees Celsius. And it's different for everything. You can get these regions where the equilibrium point is reached. Actually, those are triple points. But you can get equilibrium there as well. So a triple point is one of the is the equilibrium between all 3 phases. So you get all 3 of them at once. But anyway, again, not something that we're going to do anything with here, but it's just for your interest, I guess. And that takes us to the end of that. I believe this is the last, yeah. So here we talk about what is humidity. Humidity is this idea that liquid escapes, the particles in a liquid escape into the gas above it because of the pressure. If the pressure is low above the liquid, then there's not much air or not much gas holding that liquid in. And so some of the particles from the liquid will escape into the air above it, into the gas above it. And that creates a different feel to the air above it. If there's water in the air, it feels different. It feels heavier, it is heavier. And your body can't sweat as well because if there's a lot of water outside your skin, the water inside your skin is being pushed into the skin. It's being prevented from leaving your skin. So you can't evaporate your sweat. And so you, instead of that sweat evaporating off of your skin, it just kind of sticks to your skin, or it never, sometimes it never even leaves your skin. So, so this idea between pressure and humidity, they're very, very related to each other. As the temperature of the air increases, it actually allows more water to get into it. It can actually hold more water. And this is what we call the saturation vapor density of air. At negative 50 degrees, it has a very low saturation vapor density. So air cannot hold very much water at low temperatures, which is why in the winter it's so dry. It just can't hold water. As you get higher and higher in temperature, it increases. This is 0.039, and that's, I think, in grams per meter cubed. But when you get up to, and this is in degrees Celsius, so the hot days in Nebraska are in the 40s, up up close to 50 maybe. This 51 is like 10,000 times as much air as it can hold in the winter time, right? In the winter time, we don't get down to -50, but -10, -20 easily. And that's pretty low. That's not holding much air, not much holding much water at all. But a lot as you get hotter and hotter and hotter. Even in these temperatures, it's holding a lot of water. So it can get very humid. And the percent of humidity that you measure is determined by the temperature. So the temperature, if it's let's say it's 30 degrees outside, which is a warm day but not hot. It's like a nice fall day maybe, or a nice spring day. It can hold 30 grams, 30.4 grams per meter cubed. So if you do have 30 grams of water per meter cubed in the air, that's 100% humidity. If you had 15, then it would be 50% humidity, and so on. So that's how they calculate what they call the relative humidity, I guess. So here they talk about partial pressure being equal to vapor pressure, and they actually calculate the partial pressure. Partial pressure is the number of molecules per volume. So that's this N over V. I believe that's what partial pressure is. I'm trying to remember if that's correct. It says it right here somewhere. Yeah. Where do they define the partial pressure? I can't remember. Well, anyway, in this one they calculate the number of molecules per volume, and then they convert that using the density of the gas of water. So if that pressure ends up equaling if that ends up equaling the vapor pressure, that's 100% humidity. So, but that's all done. Here they actually just run through it step by step, calculating humidity, and then also they also talk about dew point. Now, dew point here is something that you look up. And it's not in that one. I don't know where they're saying this. I don't know if I have you do anything with this, but let's take a look at it. All of this stuff is nothing. I never took a class in weather science at all. So these are things that I always have to relearn every time I come and teach them, because I never remember how they define these things. Calculating humidity and dew point. So the percent relative humidity is the vapor density, which you get from the ideal gas law, divided by the saturation vapor density, which you look up in the table, times 100. And that gives you the percent relative humidity, which is what I said before. Then the dew point, so the dew point is where the relative humidity hits 100%. So if you look at this table here and you say, okay, I've got, let's say I have a temperature of 10, and my temperature right now is 10 degrees Celsius, and my humidity, the amount of humidity I have is 6.8. grams per cubic meter. Then I would look on this table and say, this is my temperature now, and that's my humidity right now. So if my temperature drops to this temperature, 5, then I'm gonna have 100% humidity. So that's my dew point. So the dew point is whatever temperature you would have to drop to for the humidity that you have to become 100% humidity, if that makes any sense. If you're taking an actual weather class, they give you a chart that just shows you the dew point for every temperature and humidity. And it's a really confusing chart because I had to teach that in physical science. It's really confusing. But anyway, that's the idea. The dew point is the temperature you would have to drop to for the humidity that you have at the temperature that you have to become 100% humidity. And that's what they're talking about there. And I can't remember if I give you any problems like that. I don't think so, but let's take a look anyway, because that's the end of our chapter there. So this is chapter 13, and that's the end of chapter 13. Oh, this one has, we actually have a question in here on entropy, and I don't think we even covered entropy yet. So I need to remove this question. Question 18, apparently. Yeah, there's nothing in here that has that. Let me remove question 18 from this in here. So does anybody have any questions for me as we finish up here?
I don't
Any
think so.
questions? All right, well, I'll turn you loose with the homework. Enjoy. And we will meet again on Wednesday and figure out what we're going to do from there. Have a good day. If any of you are going to have troubles doing the final by the end of this week, please contact me as soon as possible. We'll figure out what we're going to do for you, help you to get that done. Enjoy the rest of your week.
Thank you, sir. You too. We'll see you later.
Thank you.